300 is getting a new number next term. It'll be 3310. And with that, there will be some changes that come on board. So feedback from the students is really, really helpful. We don't provide any kind of incentivized, filling out the survey kind of thing. We just hope that you take the time to do that. Okay, so let's move on into a little bit of a review, an open Q&A about the class material. So by this point in the class, I've hoped that you've had exposure to these different items that were part of the class objectives. This is the type of information we provide to the accreditation agencies that basically come through and give a rubber stamp saying you are a certified biomedical engineer and you're coming from a certified program. And this is something that's very consistent across all biomedical engineering programs in the country that want to meet these standards. And so getting an accredited degree means that they feel like you should have exposure to this material. I know that this class is somewhat notorious in the curriculum for its difficulty. I think by the end of the semester, you have accomplished a certain level of proficiency, which makes you capable of communicating with any engineer in any discipline through the commonality of this physical phenomena that takes place. If you talk to an aerospace engineer, they're going to have an understanding of fluids just like you do, only they've been focused on aerodynamics, whereas you've been more focused on liquid phase behavior. We're looking at the micro scale, they're looking at very macro scale type behavior. If you talk to a chemical engineer, they will know a lot about mass transfer, and we've learned a lot about mass transfer. And so they will be very proficient in convection and diffusion, just like we are, combining that with reactions. And so, we're hoping to position you guys so that you've achieved all this material through the biomedical lens. But nonetheless, you're earning your stripes as a true engineer, and you have the ability then to take classes in other disciplines or interface with engineers from other disciplines through this common material. So it really is important for your engineering background. And I know I never thought I would use this material again, and I use it all the time. And it's hugely influential in just about every sort of sub-discipline of biomedical engineering. If you go into imaging, you have to think about things like water diffusion for MRI contrast. If you go into cardiovascular engineering, you're thinking about fluid motion and turbulence in blood vessels, things like pressure differences across cardiac valves. If you go into tissue engineering, you're going to have to think about things like cytokine communication, hydrogels, and the embedding and hindered diffusion of molecular movement between cells. So, it comes up again and again. So there are some very fundamental math principles that we've hoped that you've gotten at this point, and these are the things that we tend to have crop up in test material because we really want to get you comfortable with converting between different coordinate systems, using the generic form of a mathematical equation through the use of Dell and Laplacian operators, and then being able to plug in for the specific geometry of interest and recognizing what that appropriate geometry would be. Being able to integrate different equation forms, substantial derivatives, we haven't worked with too much other than the understanding of what they are and how you can simplify down a field equation into something that's of one dimension. So we've simplified that down to just one component with respect to space or one component with respect to time. The non-dimensionalization of variables and parameters has been very important in this class and something that allows us to get an order of magnitude relationship between all of these different phenomenon, whether it's momentum transfer or mass transfer or heat transfer. A big component of this class has been simplification of PDEs down to ODEs. and understanding how and when you can do that. And then sort of this analysis of multivariate relationships that comes from that. So let's start way back at the beginning, and just kind of march through some of the material we've had, so you remember and think about how we went about discussing all of these things. So the first section of the course was thinking about fluids, and we started from a very control volume conservation type analysis. We started really from 2210 type of understanding of fluids, thinking about them as a box of material in which things come in and out, and that allowed us to come up with these conservation relationships, which then eventually progressed into the differential form. So we went from an integral form to a differential form in our understanding of how this worked. And with that, we were really first having to recognize that you have the fluid motion occurring, and there are different perspectives that you can take. You can follow a particle through time and have a moving coordinate system, or you can have a static reference frame and look at stuff that's just coming in and out of a particular area, volume. And so that Eulerian form, the latter form, is what we used for the majority of the class. It was only a few times with respect to some of the mass transfer where we saw examples where you might want to have a changing reference frame. Okay, so we first of all had to come up with that Reynolds transport theorem. And in doing so, we were looking at how you come up with those surface integrals and how you think about something coming in and out with respect to a normal vector, which is your surface that you're crossing. So if you think about this coming in and coming out, and you're looking at that with respect to the normal vector, we had a sign change that occurs if you're just looking at the two planes of interest in a single dimension. So we had a sign change, which allowed us to think about in minus out, right? So that then allowed us to think about these fluxes just in terms of simple positive and negative directionalities. We talked about things like average velocity and how you go about calculating average velocity. So if you have these streamlines that are crossing a plane of interest, then if you want to integrate across that plane, you can think about each one of those streamlines having an independent property of velocity. And they're not always the same. So especially if we're thinking about with respect to a plane, and we're looking then at a cross-sectional area, we got familiar with that parabolic profile that would arise from that no-slip condition. If we're talking about a cylinder and pipe-driven flow, then we had that beautiful parabolic, fully parabolic shape that formed, which allowed us to then consider how we might use this to consider volumetric flow rate within a tube and use that average velocity relationship to come up with a mass flow rate. And this was a big component of at your section, being able to just come up with these conservation relationships, calculation across a plane of interest to get an average value, and using that to then say something about conservation of mass. This divergence theorem, we really touched upon, but really it was a way to flip back and forth between scalar and vector form. And that is really underlying what's going on with all these surface and volume integrals. So I don't think you really had to apply this necessarily in any of your practice problems, but just understanding where this comes from and the fact that these two things can be changed back and forth through just a mathematical relationship. Okay, so then we talked about properties of fluid and viscosity. And the property of viscosity then comes up again and again, especially in the last third of the class. And this relationship between viscosity and the partial derivative of velocity is extremely important. And that's how we came up with these relationships of shear stress and wall shear stress, which arises through that property of viscosity times the partial derivative of velocity with respect to location. And that allowed us to look at these types of relationships where for a parabolic profile, whether you're looking at this in terms of a rectangular channel or a cylindrical channel, how this then would give you a linear relationship for your shear stress. Okay? And so this was a really important concept. Do you guys feel comfortable about this type of relationship? And how, with your no-slip condition, you're getting maximum shear stress at the wall. And then as you're moving away from that wall, you're going to have a minimum value at the center line. That's the furthest point from the wall, which means you have the least amount of resistance. So if you think of that shear stress as really a consideration of the friction between the fluid and the surface of your channel, then you're going to have the minimum amount of friction at that center line. You'll have your maximum velocity at the center line for the same reason, because you have less resistance at that point. Okay, so thinking about the curvature of that and how those two things are related, parabolic for the velocity and linear with a minimum for the shear stress. That's a really, really important concept. And we actually took advantage of this knowledge, right? Once we had this information, we could say things for boundary conditions about points either at the wall or at the center line. And that's extremely useful as well. If you had information about the shear, or there was a way to acquire that information about the shear or the Vmax, then that was really useful for really calculating the rest of these relationships. So we had all these conservation relationships. We had conservation of mass, conservation of linear momentum, and conservation of energy. And again, we started with sort of integral form, and we then would move into differential form. So some of you may think about this easier in terms of these surface and control volume integrals, and others of you may find it easier to work in partial derivatives. But we basically used those two mathematical formulations together to analyze our different situations. And of course, the culmination of the fluid behavior is the Navier-Stokes relationship, which are equations, which really encompass all of this information together. So we came up with a set of equations which takes into account substantial derivatives and x, y, and z components for rectangular coordinates of the Navier-Stokes equations. And we reduced this down for incompressible constant viscosity laminar flow, the very specialized situation where we could then really collapse the Navier-Stokes equations into this operator differential form, which then we used to simplify for specific circumstances. So the first thing we would do is we'd ask which coordinate system we were using, so we could plug in appropriate operator substitutions in here. We would ask questions about known pressure drops, whether gravity was relevant or not for horizontal flow, whether viscosity was important or not, and whether it was steady state. And that allowed us to drop out different terms for this and make it more and more simplified so that we could solve it. Okay, so there were a lot of examples of this in, I believe it was Unit 3 of the lecture notes, and moving into Unit 4 as well, where we started with the Navier-Stokes, and then we said, okay, what are different things that we can consider? With Poiseuille flow, the consideration was cylindrical pipe-driven flow with a pressure gradient. So if we have a known differential between the opening, the inlet and the outlet of the pipe, then we could reduce down, based on the geometry, information about the volumetric flow rate, the knowledge of that parabolic profile, and simplify all of this down into a very, very convenient relationship that we could use. So this cylindrical geometry in the Poiseuille flow is extremely useful. I've got to say, Dr. Ethier loves for this to crop up on test questions. So I think understanding how you arrive at that is useful, and how you've applied it in your problem sets is also useful. Eulerian flow is the condition of no viscosity. So that second Laplacian operator, that second derivative term, drops out. And we're looking at just a pressure differential and a gravitational term to characterize fluid behavior. Bernoulli's equation, again, is a very simplified relationship. And writing this in a very, basically a integrated form here, we could consider pressure drop, knowledge about the potential energy that is available through a change in height, and then the information about the velocity at each location. Oftentimes we had to gather that information about the velocity through knowledge about change in the cross-sectional area. So we used our volumetric flow rate relationships to come up with one of our V's, solve for the other V that way. So again, knowing when it's appropriate to use these different things. So Poisson flow, only for cylindrical coordinates. Eulerian flow is only when there's inviscid flow, so viscosity has to be eliminated. And Bernoulli's equation, there were a number of things that had to be satisfied for Bernoulli's to be used. And being able to recognize when those take place. It has to be incompressible. It has to be inviscid. It has to be steady, fully developed. I think all of those have to apply for that situation. Okay, so then we started moving into sort of more realistic flows. This was Unit 4, where we considered drag forces, viscosity, everything that would slow down momentum. So up until this point, we've been looking at this as sort of momentum being sustained, inviscid, idealized conditions. Now we're starting to look into those drag forces that really start to act on objects and interface with the walls and the geometry of our system of interest. So one of those, if you're looking at very, very, very slow flow, superlaminar, then you can have creeping flow where you have sort of a pressure differential leading to sort of an instantaneous change in velocity. This has to be essentially, time is totally eliminated from the equation here. Gravity is eliminated from the equation here. Our Stokes law for a spherical object was one way in which we could calculate drag forces. And remember, the drag force calculation can occur in two ways. You can think about a static fluid and a moving object going through that fluid and encountering that resistance, that friction, because of the fluid environment on its movement. That's more like our term 2 test where our cell was falling through a liquid, right? So the liquid wasn't moving. It was the object moving through the liquid. But it turns out that the calculation of that is totally equivalent to a stationary object and fluid moving past that object. So you can use Stokes' law either way. And you can think about those drag forces either way, either a stationary object with fluid moving across it or a moving object with stationary flow. And we took advantage of this to actually calculate our diffusion coefficients in our mass transfer section based on that same relationship, because then the Brownian motion that's occurring is basically accounting for the viscous environment of the fluid that those molecules are bouncing around in. So we're considering these idealized spherical molecules and that thermal energy involved with their movement. That has to basically follow Stokes' law. And so that was the Stokes-Einstein relation that came up with our theoretical diffusion coefficients. Our friction factor. So this is something where we wanted to account for wall shear stress. And by doing so, we were first considering that in terms of our Blasius solutions, our movement across a plate, and the viscosity kind of helping to develop that boundary layer. But ultimately, we were able to use that to come up in Wednesday's class with the Chilton-Colburn relationship, which allows us to equate that skin friction factor to these J factors for heat and J factors for diffusion, and we can totally relate those things together, which was really, really cool. All right, moving into diffusion. With diffusion, we started with that binomial distribution. Remember, Alex was hopping back and forth in front of the class, and that random motion which was occurring, which ultimately leads to movement in a particular direction. So we start with binomial distribution with discrete time and length steps, which if you take the limit as we consider a larger and larger situation, approaches the Gaussian distribution. And we could take advantage of that Gaussian distribution for a number of different ways. One was to say if we're starting with a unit amount of material at t equals 0 at your origin, then over time, we're looking at the dissipation of that that's going to follow a normal Gaussian distribution with just the variance spreading as a function of time. And that is what this probability-based calculation of concentration comes from. Okay, so that was one way in which we could calculate concentration under a very specific situation, which takes into account both time and space in 1D. We also talked about how if we wanted to do an unsteady solution and we had some arbitrary sort of starting distribution, we could take advantage of this Gaussian distribution to actually superposition integrals together and have the combination of those. Yes?
What was N naught?
That's the number of particles you're starting with. And that's constant in the system. So this is a probability times number of particles, which is then leading to a concentration. So that is for, that's a really nice relationship, but most of the time we're interested in more macroscopic behavior where we're just looking at fluxes, and the driving force of those fluxes was the gradient. So remember I said if you're starting with a lot of particles over here and none over here, that driving force through molecular interactions, they're going to bounce around and try to equilibrate to the space where there's fewer molecules hanging out. And in doing so, we're having a spreading occurring from a very dense region of particles to a very sparse region of particles. And that driving force then is reflected in Fick's first law, going from high to low concentration. And it's going to be a function of the diffusion coefficient as well. And then we could actually use Fick's first law to derive Fick's second law, where now we're taking into account change in concentration as a function of time. And we now have a second derivative, our Laplacian operator, which we had to consider here. And if we want to account for fluid velocity, if we were going to account for chemical reactions, all of those things collectively together, we could come up with a master mass transfer equation, right, which under different situations you would have to drop out terms and consider whether it's steady, whether convection was present, whether there was a reaction present to eliminate terms with respect to this. Now, the only time we really had to consider this fractional, this mass fraction was with respect to the gas situation and that bulk motion of the gas, which, of course, is what hung up a lot of people on the term test 2 with that particular problem. We then have also talked about the analogies with heat transfer. And so this last section of the class, we were relating Fick's first law to Fourier's law of heat conduction. We were relating our convective mass transfer equation to Newton's law of cooling. And then we talked about a third specialized form radiation, which we really haven't discussed in that class and something you don't have to worry too much about. So the equivalent of N sub A, your flux, is going to be Q over A, your heat flux. And the equivalent then of your convective mass transfer coefficient times the delta C is going to be your convective heat transfer coefficient times delta T. And here the conduction, the equivalent of your diffusion coefficient for this heat flux is going to be K. Now, there's a great Piazza question about K versus alpha, which I'll get to in a second here. Okay, just to reiterate this, everything we did for mass transfer can essentially be applied to heat transfer. If we had a reaction term in our mass transfer, we can have an exo or endothermic reaction term in our heat transfer. So you really can come up with the same sophisticated temperature profiles as we did for concentration profiles. And all the different methodologies that we discussed in terms of unsteady diffusion are applicable to unsteady thermal diffusion as well. Okay, so let's talk about this alpha term. Because the question on Piazza was, I'm confused when we use K, when we use alpha for heat. Why isn't that D is equivalent to both of these? And it really comes down to, if my understanding of this is correct, it comes down to the fact that thermal diffusivity is really going to be a function of the conductance of energy that a particular material is capable of doing, as well as the heat capacity of the material. So let's talk about water, okay? So we can conduct heat through water. And that conduction of heat is occurring because as you're injecting energy into your control volume of water, you are able to excite the molecules, right? And so they're going to be bouncing around more. And as they're bouncing around, they're going to be colliding with one another and exchanging energy. And so you're able to impart this exchange of energy into the system. But each material of interest has a different amount of energy that's required to increase it by 1 degree Kelvin. That's known as the specific heat capacity. And so it turns out in order to have thermal diffusion, where you have this Brownian motion and you have this bouncing around of energy, you have to consider the density of the material. You have to consider the specific heat capacity, which is how many joules it takes per gram of material in order to raise it 1 degree Kelvin. And then you also have this property of thermal conductivity. And so because of this feature of heat, when you're looking at your heat flux, you can consider that conduction term alone, which was what was on the previous page here, this K. When you're talking about this differential energy equation, you still can write it just in terms of K, which you could pull this out of this divergence operator and have your K times the Laplacian of T, and that's looking just like your diffusion times the Laplacian of C, right? So that form of the equation is identical, but then on this side of the equation you have this rho Cp, which is accounting for both the density and that specific heat capacity. So what we tend to do is instead isolate, and I'm sorry, this oval is a little offset. We tend to isolate this rho Cp by dividing both sides of the equation by it. And in doing so, that just allows us to clump all of these coefficients together into your alpha term. And consequently, your R sub A equivalent, this Q dot term, has to have a rho Cp in the denominator. Okay, so it really kind of depends on how you want to basically take into account this density and the specific heat capacity. You can leave it over on the right-hand side, and then you can consider your K just like you would your D. But you have to keep in mind that really, in order to account for your endo or your exothermic reactions that's occurring within the volume, this is your homogeneous source of thermal addition or subtraction, then you would have to account for that rho Cp somehow. Okay, so oftentimes what we do is we're looking at steady state. So if this is 0 on this side, it doesn't matter if your rho Cp is there or not, you wind up dropping it out, just like the diffusion coefficient drops out under many of the steady circumstances. But that's, I'm hoping, helps to address that question. Is that a little bit clearer to you guys? on the alpha versus K issue? Yeah? Okay. All right, I just put this slide up here because I thought it'd be useful to remind you that when we started looking at membrane-based transport, we had this relationship for Fick's first law of membranes, which is a P delta C, which is very, very analogous to our heat flux. And the fact that we could have multiple things in series allowed us to consider, that's when we started introducing this idea of resistance in series for mass transfer, which was really useful when we got to heat transfer to see how you could have resistance in series with heat transfer as well. Okay, so some of the last portion of the class, which I would say you can expect on the final to see something that you haven't been tested on yet, which basically will consist of things like transient conduction or diffusion, as well as convection. Those are things that we hadn't yet covered for term test 2. So just to talk about some of those items. For unsteady methods, one of the approaches that we talked about was the semi-infinite medium approximation. And really considering that somewhere far away from your surface, when you have an instantaneous change in your system at the surface, you're going to assume that very far away, at least for the time and length scales that you're interested in for the particular problem, that you're not going to have something changing far away. You can assume that that's constant. And you're going to have like basically a local buildup of heat or concentration at that surface, if it's releasing from the surface, that will accumulate as a function of time near that plane. And so that we can consider that sort of with increasing T, how you might start getting a buildup of mass or heat at that surface. Now, it turns out that because of the orientation of these unrealized concentration and temperature changes, you can actually have movement into the surface as well. We didn't really talk about examples of that. We're always talking about patches releasing drugs, or the UFO heating up the ground and it penetrating and warming up the soil. But there are examples where you can actually do the reverse, where you can have a drain on your system that way. We didn't really discuss any examples of that, but it's just all based on whether your C sub S or your C sub naught is greater in terms of the directionality of that flux. We talked about the use of charts. So I know there's some angst about the use of charts on the final. We're pretty lenient on if you're going to use the charts, the value that you basically interpret based on the way you're drawing your line to the axis, bless you. Realize that you can use these charts for temperature and concentration changes. You can use this for when your BO number is greater than 0.1. You can calculate the BO number, which is essentially, I think, the inverse of this relative time component, and use that for calculating those things. Oh, no, I'm sorry. Inverse of M. Thank you. Inverse of M is the BO number. And if that's less than 0.1, then you can use that lump parameter analysis. We discussed how this is all relative to the origin. So if you're considering slab geometry, you have to realize that this is going to be symmetrically diffusing towards the center line of that slab geometry. That's why for those problem set examples where you have a change on one surface, you don't have the equivalent change on the other, it's inappropriate to use the charts in that particular situation. Okay, the last part with all of these different modulus and numbers and ratios and pi groups that we talked about was all talking about this, this issue of the boundary layer. And more or less, we discussed this with respect to a flat plate. There's a different set of equations in which you could apply this for a pipe or cylindrical geometry. And that one table I had in the lecture notes provides different values for, or different equations for locally determining laminar and turbulent Sherwood and Nusselt numbers for the different geometries. We talked about how this convection that's occurring off the surface is really encompassing this convective heat transfer or mass transfer coefficient. And in this case, we know that it's locally a function of the Reynolds number. And so these convective mass and heat transfer coefficients are really kind of abstract. The diffusion and conductivity and thermal diffusivity, these are things that are really features of the material. They're well established. You can look them up in charts, and they're pretty straightforward. When we're talking about convection, it's something that's a little bit harder to grasp because it's very dependent on how fast the fluid is moving, what the fluid is composed of, what kind of differential exists in the system for your heat or your temperature or your concentration. So these are very context-specific coefficients. And you can sometimes find tables available for particular circumstances where they're very well defined, but they're very hard. And so we use these information about these boundary layers to come up with calculations for these convective transfer coefficients. Just briefly to mention, one of the ratios that we discussed was the Peclet number, and that was a relationship between convection and diffusion. That was a little bit different than our boundary layer consideration because we started from the overall mass transfer equation, and then we reduced it down for one dimension in our spatial directionality. We eliminated the time component, and we solved things that way instead of considering our dc dt or a zero on the left-hand side. Okay, so we had all of these. I encourage you, if you didn't attend the last class, to at least look at Wednesday's lecture notes where I went over all of these in great detail, because it's really important that you understand when these are applicable, how you would use these to determine what is dominating in the system. These are very sort of intuitive, ballpark things that, as an engineer, they're extremely useful to be able to say, hey, my Prandtl number is really big here, therefore I don't have to worry about thermal diffusion. Those kind of estimates. Reynolds number. My Reynolds number is 2 million. I can't consider this to be laminar flow. This is sort of the language that we want you to be able to apply in very context-specific examples. Okay. I know you guys want to hear this slide. Things to not worry about on the final. This semester, Dr. Ethier did not have time to really go into head loss or the mechanical energy equation. Okay, that's, I think, at the very end of maybe Unit 3 or Unit 4. I think it's Unit 4, the end of Unit 4. So you do not have to worry about that. There was a question on Piazza about using the Moody charts. I don't think you really saw examples of that, or it wasn't discussed in detail in the class. So I don't feel like you should be responsible for that material. Current exchangers, that's something I normally devote a whole lecture to. Instead, I just gave a few slides on it in the last class to expose you to that material. You're not responsible for it. You may see some current exchange problems on old tests, so don't panic if you see those. You don't have to know those types of questions. Things like separation of variables or Laplacian transforms, things that we use to derive other methodologies. You're not responsible for knowing all of the mathematics behind that or having to apply that yourself. I talked about how radiative heat transfer is sort of a special circumstance for heat transfer. We really never had examples of that in the practice problems. That's something that could be added in series with other heat transfer. You don't need to know it for the final. So Dr. Ethier would like to say that in terms of what to study for, you know, the entire syllabus, I would say focus on, first of all, things that you have not been tested on yet. Consider that the material is cumulative in nature. You know, this Chilton-Colburn relationships build upon stuff back in February. You have to be able to kind of carry that material forward and use it all together. So really trying to divide it up into specific units or specific examples is hard. And I've told people that Dr. Ethier's questions, he loves to have things build upon like multi-part type solutions where you have to calculate one thing in order to get you to be able to use another relation, to get you to use another relation. So it's a little bit of a circuitous route to get from point A to point C. And usually a way to think about that when you're setting up your gym analysis is think about the physical system, what you're being asked to solve, and ask, what information would I need to get that? Well, they didn't provide me with, you know, a volumetric flow rate. Maybe I need to calculate that somehow. How would I calculate that? Well, I need this cross-sectional area. Well, how would I get that? Well, maybe I can do that with Bernoulli. So, you know, like, you've got to kind of work backwards to ask what information was given to you, what do you still need, and what conservation or physical relationships can help you get from point A to point C through some intermediate steps. And so that was like the type of thing, like in last class I was talking about, that example of the DNA hybridization. I mean, they had information about their Reynolds number, and they wanted to get to kinetic reaction rates, right? And so they went through this path of first calculating velocity, then from velocity calculating friction factor, from friction factor calculating a J factor for mass transfer, from that being able to calculate a kinetic reaction rate. So, you know, those types of things are the way to think about some of these test questions. Okay, you guys are packing up. Yes, questions?
How many test questions?
4 test questions.
And is it in this room?
It's going to be in this room. I think it starts at 11:30 on Monday. You'll have, of course, the full exam period until 2:20 for it. It's open book. You can bring anything but communicating devices. I would, if you don't have a textbook, Xerox those charts. The appendices are extremely important for the latter portion of this class with all of those charts and error functions and all of those things. You want to be able to have that material on hand. Be organized with your materials. I saw some beautiful example in office hours of people that had binders where they had organized things by tests, by lecture notes, by quizzes, by problem sets. If you can flip to things quickly, that always helps. The time pressure is a little bit alleviated for those of you that feel like you haven't been able to execute well on tests because of the time constraints. Because you're going to have, it's like a double test, but you have almost 3 times a normal class period. So that should help a little bit, relieve some of that time pressure. Other questions? Yes?
So if you write on your gym analysis, let's say you have to use Bernoulli equation, but you shouldn't, actually, do you take points off for that?
Wait, say that again?
If you put something in gym analysis that we're not using, do you take points off?
If you put something in the gym analysis, but then you don't use it when you solve the problem?
Let's say a problem shouldn't be solved with Bernoulli,
Right.
and I write that we need Bernoulli for this problem. Is that...
That might cost you in points, yes. So don't just vomit everything on the gym analysis. Yeah, because if it's incorrect, that could be points deducted. Okay? So I will upload your rankings this afternoon. I haven't compiled the grade sheets, but I will do that, so don't email me.